Our today's speaker is Dr. Muhammad Wakil Shahzad, and I must say he has a very impressive CV. He is presently a senior lecturer in mechanical and construction engineering department at the Northumbria University, based in Newcastle upon Tyne, of course, in the UK. He has previously worked, say, about for 5 years since from 2014 to 19 in Saudi Arabia in a very prestigious institution called King Abdullah University of Science and Technology. They have a center there, Water Desalination and Reuse Center, and hence it attracted our attention as well. So he has a good work experience over there as well. He has expertise on hybrid desalination processes, heating and cooling, solar thermal energy storage, and renewable energy related aspects, which he has been researching and has got a bit hands-on experience as well. He has a number of awards, which is a bit mouthful, like Sustainability Medal 2020, Global Innovation Award 2020, National Energy Globe Award Saudi Arabia got twice, back in 2020 and in 2019. Excellence in Leadership Award 2019, and then he has IDA Environmental and Sustainability Award received in 2019. Apart from that, as an academic, he has been having his presence felt at a number of international leading conferences, where he has been not only once, twice, but 3 times his paper has been awarded as the best paper at several international conferences. Not only that, as an academic, that's fine, but what really matters is to translate your research into practice as well. So he has been successful along with his team in commercializing some of desalination processes through a spin-off company as well. He has got 11 international patents and about 200 publications, including lots of journal publications and so on and so forth. He's member of several international professional organizations, and today he's going to talk about solar-driven dry hybrid water treatment systems for future water supplies. Phew. Wakil, I'm sorry if I have missed anything, so I do apologize in advance. So the floor is yours. Over to you, Wakil.
Okay, so thank you very much, and thank you very much, Professor Fayaz, for your kind words. And thank you very much for giving me this opportunity to present at this prestigious platform to share my research. And also thanks to Professor Albert for all this coordination. Yeah. So good afternoon, everyone. Today I'm presenting our solar-driven tri-hybrid water treatment system for future water supplies. And as Professor Fayaz mentioned, so I'm working as a senior lecturer at Northumbria University, UK. I would like to start with the United Nations Sustainability Goals because it has a very good relation or connection with the water treatment process, more specifically. So as we know that there are 17 goals and 169 targets, and it covers actually all the aspects of the life, from poverty to hunger to energy, almost every sector of the life cycle. But if we zoom down to these all 17 goals, actually there are the 3 major goals. Those have very good interlinks between all these 17 goals. So those 3 goals are clean water and sanitation, affordable and clean energy, and climate action. So these 3 goals actually have a direct or indirect relation with all 17 goals. But within these 3 goals even, if we look carefully, the water is a major goal or the major entity that have the very strong interlink between energy and the climate action. So in other words, we can say that the water actually directly or indirectly linked to all 17 goals, and it play a very crucial role for the future sustainability. But unfortunately, most of the countries, they are actually under severe water stress conditions, and this water stress umbrella is actually increasing and covering the most of the part of the world, as we can see. So it also mentioned by 2030, this water stress level will be even worse. So let me explain a little bit. So water stress means that any country that has a water availability less than 1,000 cubic meter per capita per year is called water stress condition. And similar to the other part of the world, UK also almost like moving to that direction. So we can see some part of the UK is already highlighted as a severe water stress condition in some part of the year, like specifically in the summer. And the some part that is in moderate condition now, it is expected to reach to the severe condition by 2030. So that's why there are few planned water treatment like the plants in a different part of the UK to overcome this water scarcity in the next few years. So in terms of numbers, also very shocking, over 700 million people, they don't have access to the clean water. That is around 1 in 9 in global population. And over 400 children, normally they are unable to attend the school in each year due to the waterborne diseases. And that is around 80% of the illness are actually related to the related with the water. And similarly, over 300 million in specifically in the sub-Saharan Africa region, they don't have water and the sanitation facilities. And this picture is actually very interesting because this water stress is, of course, is mainly related to industrialization, but also there is another factor that is the people, they always try to live in the better conditions. So urbanization also playing a very big role in water scarcity. And over here, we can see that the food that normally we consume on daily basis, and most of the time, we actually don't realize how much water is consumed, and even we waste the food, but indirectly water consumed to produce that food is actually a lot of amount of the water. So for example, we can see the 1 kg of the chicken is around 3,000 liters. But I was quite shocked to see that the 1 kg of the chocolate, as you can see, it's around 24,000 liters of water. So many of things over here, we can see that we consume on daily basis. Of course, sometimes we waste as well. And we don't realize that to produce that food items, how much water is consumed. So that is actually really shocking, the figures over here. And one of the reason is actually inefficient agriculture process. And if the business as usual will continue, it is expected that by 2030, there will be a 40% gap between availability and demand. And even though there are the few like a process like a wastewater treatment and water reuse, but all these processes are even water reclamation. So these processes are unable to cover this 40% gap by 2030. And this estimation was done in 2005. I feel that maybe now we can see this gap maybe more than that because of the more industrialization and GDP growth. So then what can be the solution? So the alternative solution is a seawater treatment process, because the seawater is available, and that is most feasible and practical solution to produce water to overcome the water scarcity in near future. And seawater desalination is not new, and today around 20,000 desalination plants in over 150 countries, they are producing around 28,000 million gallon water per day. And most of the desalination process, they are operating in GCC countries and based on seawater, because in GCC countries, the water scarcity, the water condition is even more severe because of the no rain. And over here, we can see the installation of desalination process. And again, we can see that Gulf countries are actually leading because of the water scarcity in the Middle East region. And of course, the other part of the world also the water treatment process. Those are mostly based on brackish water, like a river or a lake water, but not mainly on a seawater desalination process. So in terms of process, there are two major processes. One is called thermal methods. Those operate mainly on a heat, like evaporation and the condensation process. And the other one is a membrane process. Those are mainly operating with a high pressure pump across the membrane to overcome the osmotic pressure. And of course, under these two main categories, there are few processes like thermal driven process. They have MSF, multi-stage flashing, multi-effect desalination, and some hybrid process. And similarly, the membrane process have also reverse osmosis that is mostly used all over the world. So in terms of installation, actually it varies from country to country and from region to region. And the major reason is the water availability and the quality of the feed water. Like in the Gulf region, GCC countries, a thermal desalination process are preferable. And the reason is because the seawater is very severe over there. And the turbidity of the seawater change very frequently due to the marine like ship movement and all these things, and that actually not very favorable for RO process. So that's why the thermal process are very favorable over there. But on the other hand, in other part of the world, the RO process are very favorable because they are used on brackish water mostly. But it doesn't matter whatever the process it is for the water treatment, it must match the nexus of water energy and the environment. So it means we should have water treatment process that use very less energy and also help to protect the environment. But unfortunately, today, the conventional process, they are consuming over 75 terawatt hour electricity, and they are contributing around 76 million ton of CO2 per year. And that is really a shocking figures. But if we look into the literature, the story is totally different because all the reports and the papers the published in the literature, they claim that the processes are highly efficient. So for example, if we look into the process like a reverse osmosis process, membrane-based process, there are a lot of highly reputable journals and good reports from many consultants. So everyone claimed that the process efficiency is very high. It's like they reach to the sky. On the other hand, the thermal desalination process, people are also not like a behind. So they also claim the same thing, that the processes are very efficient and they are reached to the highest limit. So now the question is, which process is efficient? Because if we just look into the literature, it's very confusing. Every process claim very efficient, but if we see into look into the energy consumption and the CO2 emission, that is also very high. So it's a bit contradiction over there. So we try to find out first that how we can actually evaluate the process. And then because if we can measure the efficiency, then we can improve the efficiency. Without measurement, it will be very difficult to find out the level of their performance. So as I mentioned earlier, that there are the three major desalination process. Those are installed all over the world, like a reverse osmosis, multi-effect desalination, and multi-stage flashing. So these are three are the largest plant in the world with their capacities and the location. I took the data from the literature. And I also mentioned over here the average energy consumption from different plants all over the world. So this around over 40 plants data from all over the world. So if we look into these numbers in terms of energy, let's say the RO process, they consume around 3.5 kilowatt hour electricity per cubic meter. And a MED plant, they consume electricity as well as thermal heat, and also the MSF electricity plus heat. So if we just look at the numbers over here, and we try to compare these processes, one can easily say that RO process is very efficient. If this is the case, that is not true statement because we forgot that if we just look at the numbers, we are comparing the dollar with dollar, but we forgot that one is a American dollar and the other is an Australian dollar, and there is a conversion factor in between. So same applies over here, that one is electricity and one is a thermal heat, so we cannot compare one to one. And so this is a major misconception that based on the conclusion that the processes are efficient. So in other words, the electricity is not same as a heat, that is not same as a primary fuel, and that is not same as a standard primary energy. And so this standard primary energy means that the fuel that is consumed at the first point in the combustion chamber and then followed by the process to produce the electricity and the heat. So this is a typical the plant. Normally, the power plant and desalination plant is actually installed together, and the reason is because if they are installed together, the most of the utilities can be shared with plants, and that actually improve overall performance of the system. So this is the typical configuration of power and desalination plant. So there is a combined cycle, a gas turbine, followed by steam turbine, and then followed by the three type of the desalination process. So now the question is, if let's say we spend $1 on a fuel that is introduced into the power plant, and of course it will produce electricity in a gas turbine cycle and in steam turbine cycle, and then some heat in terms of a bleed steam will be utilized in MSF and MED plants, and electricity for all three plants. So then how we can apportion this $1 that consumed in terms of fuel to electricity produced and to the water that is generated through this process. So this is the big question, because if we just follow in terms of the flow rate, the mass flow rate, that will not give a correct picture because that don't include the quality of the working fluid. And that is we called as the exergy analysis, because the analysis based on energetic form that only consider the mass flow rate, not the quality of the working fluid, will not give the true picture. So we try to develop the thermodynamic framework that can be used to compare all the desalination process irrespective of the energy utilization. So we come up with a figure, we call it as standard universal performance ratio. Earlier was only performance ratio, and that was based on two different forms of the energies, thermal and electricity. So we derive this formulation, and we drive the formulation and the framework to find out the conversion factor, that how we can convert different form of the energies into primary energy, bring back to the initial state of the energy, so that we can add up all the energies because all will be at the same platform. And then we can compare across the technologies because we are comparing on a common platform. And after successful derivation of this platform, we apply to the real, one of the real plant data from Saudi Arabia. So let's say this is again the same typical CCGT plant, and the fuel consumed, let's say the exergy is 100%, and 58% is consumed by gas turbine cycle, 2% is around losses, and 39 or 40% is exergy carried by the product gases after the gas turbine, and that is going to the heat recovery steam generator. So out of these, 36.8% is actually consumed by the steam turbine cycle, and only 3% is actually consumed by the desalination cycle, because the bleed steam that is bled from the last stages of the turbine is actually already produced electricity, is already done their work. So now this is almost the dead steam. But this is a very good for the desalination cycle, because desalination cycle operate at a low pressure and low temperature. So combining this, the CCGT power plant with thermal desalination is an excellent thermodynamic synergy, because both systems, they operate at high temperature and low temperature. This synergize very well to get the maximum from available. So based on this exergetic analysis, we derive the factors to convert different form of the energy into primary energy. So converting the electricity into standard primary energy, the conversion factor is around 2, and that is indirectly, we can say that around 50% of power plant efficiency. That is the typical efficiency of CCGT power plant, from 47 to 55%. But this was quite interesting, the second one, that converting the low pressure steam into primary energy. So 1 unit of standard primary energy, it can produce 10 units of that low pressure steam that is used in a desalination cycle. So based on these two figures, the conversion factors, actually we can convert the different form of the energies that I showed at the start for the 3 plants into primary energy, and then we can find out how much is the performance ratio for the different plants. So here we can see the answer. So here is again all the 40 plants that we took the data from different literature. We applied our thermodynamic framework, and we plotted this one in terms of a ratio that how much is meter cube per kilowatt hour SPE based to the thermodynamic limit. So this thermodynamic limit, why we compared with respect to thermodynamic limit? Because thermodynamic limit is the standard formulation, and that is irrespective of the process. So this thermodynamic limit is actually 1 cubic meter water can be produced per kilowatt of standard primary energy, and this is irrespective of the process. And this is a thermodynamic limit, and this is a theoretical limit that we cannot achieve. But this is a good reference to compare the existing plants. And we can see over here very clearly that all the desalination process available today, those are applied commercially, they are only operating at 10 to 13% of thermodynamic limit. So it means all the literature, they claimed that the very highly efficient and very improved process, those statements might not be true, because if we compare it with thermodynamic limit, that is a standard, the process is only at 10 to 13% of thermodynamic limit. So now we can see very clearly that we have a very big gap to improve, and all the processes are not efficient, not sustainable. We have to improve the process to get the future sustainability. So to learn the lesson that how we can improve how it was improved in the past, we gathered the data from the history. So the desalination, as I mentioned, is not new. It started from 15th century when the ship was sailing in the sea. The people drink the water, right? And the ship, they normally take 3 to 4 months reaching to the destination. So this is how they were producing the water by just like an open distiller pan. So they just evaporate the water and condense. And because of the losses, the performance was very low. And then the first jump was observed when the efficient boiler technology came into the market due to the efficient burning process. And then there was another jump somewhere when there's multi-effect desalination and multi-stage flashing because of the multi-recoveries. And also some RO process were introduced. And the last jump was observed when these processes were integrated into desalination process. And that was around 1985 when there was a big commercialization of the desalination process. And after that, until today, there's a gradual change, the improvement of the process, but there's no big jump was observed. And the reason is because all the 3 technologies are still same. Those were invented from the start, and there's no change in the technology. So the lesson learned is that we can only get the high jump in the performance if we change the technology. If we don't change the technology, just improving the process can help us to get a little bit improvement, a gradual improvement, but not the high jump in the performance. So today we are at the point that we have to work to find out some innovative or out-of-box solutions so that we can again get a high jump in the performance to achieve this sustainable the processes zone. So we started looking into the limitation of the conventional system. So as I mentioned, so there are the 2 major processes, thermal and the membrane process. So the thermal process, the limitation is the operational temperature. So the highest temperature is 65 degrees centigrade around. If we operate higher than that, there will be a scaling of the salt and the falling onto the tube surfaces. And the lowest temperature is controlled by the seawater cold condenser, and that is around 40 degrees centigrade if seawater is at 30 degrees centigrade. So similarly, the RO process are also limited by the seawater quality, and it actually very sensitive to the seawater quality, because if seawater quality change, they can easily fall and clog the membrane. But thermal desalination processes are quite favorable and robust in terms of seawater quality. Even though the seawater quality change, the process, it don't impact on the process, and the water quality, the produced water quality also remains the same. So we start looking into a thermal desalination process. So this is a typical multi-effect desalination process. So as I explained earlier, so this is a bleed stream from the last stages of the turbine, and it is supplied to the tube side of the first stage. We call it as a stage because multi-effect So it's a multi-effect, means the multi heat exchanger arranged in parallel manner. And on the tube of the on the outside of the tube, there's a seawater spray, and the vapor produced over here is actually used as a heat source to the tube side of the next stage, and this will be condensed, and the heat of the condensation will be recovered to evaporate the more water in the same stage. So this evaporation and the condensation is continue until the end. So the last stage vapors are condensed in the condenser. So this is where the limit is 40 degrees centigrade because it's cooled by the seawater. So the overall process is controlled by these two temperatures, and that's why the number of recoveries are also limited to 6 or 8, and that's why the performance is also limited. So we try to find out that how we can overcome this limitation so we can improve the process. So we come up the idea that we can actually disintegrate this condenser from the last stage, and we introduce our adsorption cycle. So it means if the last stage vapors that is typically at 40 degrees centigrade, it introduced to the condenser with not introducing to the condenser, by introduced to the adsorption cycle, we can actually bring down the temperature to as low as 5 to 7 degrees centigrade because the adsorbent, the silica gel, typically used as adsorption chiller, and it produces the water at 5 degrees centigrade. So by using the same concept, we assume that it can be the temperature can be extended from 60 degree to 5 degrees centigrade, and we can insert more number of recoveries with the same given heat input, and of course proportionally the water will increase. So here it shows that from 60 to 40 typically is 6 to 8 number of stages, but if we overcome this ambient limitation and we bring down to 5 degree, we can actually install from 12 to 15 number of stages, and accordingly the water production will be 2 or more than 2-fold improvement. So second target was that how we can improve the top brine temperature by introducing some nanofiltration. That I will come back again in the last few slides. So first I will explain that how we introduce this adsorption cycle and how we demonstrated this process. So this is a small simulation that shows that how the system works. So let's say this is a heat source that is coming out from the last stages of the turbine. It introduced into the tube side. Outside is a seawater spray. And the evaporation from the first stage is used as a heat source to the second stage. And heat of condensation is recovered and used to evaporate the more water. So this process continues until the last stage, and from the last stage, the vapors are condensed in the condenser. So this is a typical MED, how it works. So that's why the limit is 40 degrees centigrade. So what we did, we bypass this condenser and we close this valve, and the vapors are now introduced into the adsorption chiller, and it absorbs on the silica gel, and it dissolves and condenses in the condenser. So actually condenser don't have directly linked to the last stage, and this is where we break the limitation of 40 degrees centigrade, and we extended this operation temperature to as low as 5 to 7 degrees centigrade. And so we have three different patent on this hybrid desalination process. So to demonstrate this hybrid concept, we designed and we fabricated and we installed adsorption and MED plant. So we can see over here, so this is adsorption, the pilot, and it is operated with a solar evacuative collector that is around 100 kilowatt capacity, 352 meter square area. And so this is our MED plant, 4 stages MED, and 2 big pipes over here you can see going down is actually below the mezzanine floor is our adsorption cycle. So this mezzanine floor was built on the top of adsorption cycle, and then MED cycle was integrated with the adsorption cycle with these 2 big pipes. And we have the valve over here that we can close if we want to operate as a conventional MED cycle. And we also have the heat storage tank over here. So this 3 cubic meter each tank, so around 12 cubic meter hot water that help us to operate around 4 hours, even the sun is down after like evening. So this is HMI of our system, overall control. So we can see over here there's a 4 stages, and we have a brine tank, we have a distillate tank, and the seawater is coming directly from the Red Sea. and is introduced into the condenser, and then it going to the feed. It's a parallel feed MED system. So here are the results. So we can see over here, we operated almost like 72 hours at 50-degree heat source temperature. So we can see these are the temperature in each stage of the MED, and this is the temperature across the condenser, and that is around 35 degree. Also, this is the temperature of the cold water, the seawater to the condenser, and this last over here 40 degrees centigrade is the temperature of the condenser. So after these 72 hours, we open the valve, so you can see over here, and we link it to the adsorption cycle. So we can see very clearly the temperature was pulled down by the adsorption of the silica gel, but still we can see the temperature is around 25 degree, and that is a hardware limitation because we have only 4 stages, and we maintain this 50 degrees centigrade. So in other words, we can introduce more number of the stages at the bottom. There's the gap available, or we can reduce the top brine temperature to test until like a 5 degrees centigrade. And this is the water production profile. So this is a conventional MED system for first operation, and then when we linked it to the adsorption cycle, we can see the water production was boosted to around 2 to 2.5 fold at the same heat input. So here is overall results. So we can see that the result that I presented earlier on the previous slide, it is on 50 degrees centigrade, but we tested at all the temperatures to check the consistency of our pilot operation. So this green line over here, it shows the water production of conventional MED system at different heat source temperature, and the red line, it shows the water production of our hybrid system at assorted heat source temperature. So we can see that all the temperatures at all heat source temperature, the water production was over 2-fold as compared to conventional MED system at same heat input in terms of kilowatt. And on top of that, the conventional system, the limit is 40 degrees centigrade. So we don't have limit. Our system can go as low as 5 to 7 degrees centigrade. And so this was a successful demonstration of our hybrid MED+AD pilot. So then we realized that actually the process can also be hybridized with the membrane distillation system to run as a tri-hybrid system. So why this idea came into our mind? Because the membrane distillation process is actually used hot front and the cold front to extract the vapor from the feed across the membrane. So this is again the schematic of our same system, and we realize that we have a heated brine that is coming out from the first few stages, that is around about 40 degrees centigrade, and it is a pre-treated brine. And we also have the chilled distillate that is coming out from the last stages. Those are operating below ambient conditions. So this is a very good like a hot front and the cold front for the MD system. So just to remind again, so this is how the MD system works. So there's a membrane, and the hot feed is circulated at the one side, and there's a cold front on the other side, and that helps to extract the water vapor through the membrane and condense in the distillate, or condense on the wall surface of the cold front. And by using the same concept, we hybridized the MEMSES system that produced the membrane distillation. So we can see over here, this is our hybrid, and then with the MEMSES system to run as a tri-hybrid system. And we use the last 2 stages distillate as a cold front, and the first 2 stages brine as a hot front to extract more water within the given energy input and the water input. So the 2 major benefits that we were trying to get, the firstly is that if we extract the more water from the given feed input, actually we are reducing the chemical injection because the recovery will be more. And the secondly, of course, the CO2 emission will be reduced if this system will be operated in conjunction with the power plant. So we have another 2 patents on this system. So here we got the results for this tri-hybrid system. So we can see over here. So this is again, the red dots over here is our MED+AD water production. So this time we normalized the water production into liter per meter square per hour, because this will give us a very good platform to compare with any system as long as we have a water production per meter square, because the system can be a reverse osmosis or it can be a thermal system. But if we can normalize it in terms of per meter square area available, we can actually compare the system. So that's why we preferred it to present in liter per meter square hour, so that we can compare it with any other system. And the gray dot over here is actually membrane distillation water production. That is not consuming any form of the energy, because it's just more water extraction from the reject of our hybrid MEDAD system. So this chart over here shows the overall results. So the blue line is the MED water production. The gray line, the orange line is MEDAD water production, and the gray line is tri-hybrid MEDAD plus MD water production system. So we can see very clearly that the hybridization boosts the water production to over twofold, around 2.5-fold. And with the MD hybridization, we achieved another 25% water without consuming any energy. So if we go back to the chart again that I showed at the start, we can see again, we marked our point over here, and we were able to achieve around 20% of thermodynamic limit as compared to 13% of conventional systems. Still, we believe that it's not a sustainable zone. We are expecting to achieve around 30% of thermodynamic limit, because most of the thermal system they can achieve, like IC engine, or even I showed the power plant even achieve until 50% of efficiency. So that is, we call it as a bit sustainability zone. So we have to try. It's still not a excellent system. We have to try again to achieve up to like 30% of thermodynamic limit. So we also did the life cycle costing analysis, and we compare it with the conventional system. So we can see that our system was able to produce the water at around $0.4 per cubic meter. That is one of the lowest water production cost as compared to other systems like RO, that is around $1 per cubic meter. So our research is not only limited to the labs. We spin off the company based on our 3 patents, and we call it as a MEDAD Technologies. And we got our first contract to install 100 cubic meter water per day plant. And that plant was commissioned in 2017. And after successful operation of this plant, we got another contract that is around 5,300 cubic meter per day capacity. And that will be installed at Jammu. And let me tell you also that this Jammu is the world's largest desalination facility, where they have all RO, MED, and MSF water treatment system. And the beauty of this system is that we will use the reject from their RO, and we will use the waste heat from their flash tank and from the other system at the plant, and will boost the recovery from 40% to 59%. So it means we will produce around 19% more water without consuming any energy. So that was the biggest trigger for this contract. And we're supposed to commission and install this plant by December 2021. But because of the COVID, it was delayed, and we are expecting the commissioning by next year, mid of next year. It's in process now. So in terms of future roadmap, so we are here where we already have like a successful commercialization of our technology, but of course, we are looking for some zero liquid discharge process. We have another patent on that, and we are trying to integrate our system with ZLD so that we can produce 100% zero liquid discharge system for the future sustainability. And in addition to that, we are also looking for some grants. Those are available for solar thermal desalination process. And also we have a channel to the market, like working with advanced water treatment technologies company, and also the SWIC in Saudi Arabia. So our technology was highlighted on almost many media, like Nature Middle East, on Yahoo Business, New York Times, and Arab News, mentioning as a most sustainable process and most environment friendly process in terms of water treatment. We also received many awards like a MED Sustainability Medal 2020, a Global Innovation Award 2020, IDEA 2019, a G Aramco Global Innovation Award, Energy Global Award, and the Global Tiger Sustainability Award. And this is the book that we have on our desalination process that approaching sustainability in GCC region. So with this one, thank you very much. And I'm here if you have any questions or any point that we can discuss here. Thank you very much.